Hello. So up till now we have covered the derivation of heat conduction equation and its various forms when we apply the various assumptions on the heat conduction equation. Essentially generalized three-dimensional unsteady heat conduction equation in Cartesian coordinate system. And so we have seen now up to now that just a recap that for Cartesian coordinate system let's say our body looks like this, and assume that its length is L in x direction, h in y direction, and w in z direction. So we can see that there is no change of area in x direction. So area is h into w and is independent of x direction, we can see from here. So and assume that there is temperature difference in x direction, and because of the temperature difference heat is flowing by conduction. Okay, so it means temperature will be a function of x, and assume that it is insulated from all the other sides like in y and z direction, so heat will be flowing only in x direction. It means temperature will be function of x, and on what other parameters the temperature can depends, it will be time. As we have mentioned previously also that temperature, we have, when we are specifying temperature, we have to specify the location as well as the time on which we are specifying this temperature. So for this type of system where there is Cartesian coordinate and area is not function of the heat flow direction, in that case the heat conduction equation becomes like this. One by alpha del T by del T. Alpha is thermal diffusivity, Qj is watt per meter cube, that is the volumetric rate of heat generation, K is thermal conductivity. This we have seen. So this is one dimensional heat conduction equation. So if we see in cylindrical coordinate system, let's say assuming one dimensional heat flow only, in the cylindrical case there can be two cases. Suppose this is a cylinder, this is the side view, and it is insulated from its lateral sides, and this is the R direction of this is the x direction. Okay, and this will be its cross sectional area. Theta direction. Okay, and suppose we are maintaining temperature difference along its length, so heat will flow in longitudinal or axial direction. So first case in cylindrical coordinate system is heat flows in axial direction. For that case, temperature will be function of x and time, and since the heat is flowing in the x direction, and in the x direction area is constant at every location, at every x area is constant. And what is that area? Area is pi by 4. Suppose d is the diameter of the pipe, so pi by 4 d square, and it is independent of the length. Okay, so we can write the heat equation again, like 1 by a in generalized form, 1 by a times del t by del x. Since we are considering only one dimensional heat flow, there is no change of temperature with respect to theta. There is no change of temperature with respect to theta as well as with respect to r. Only one dimensional case we are considering. That's why we are writing change of temperature with respect to x only. So Qg by K 1 by alpha del T by T. Since area is not function of x, area can come out and it will get cancelled from it. So again we get del square T by del x square plus Qg by K 1 by alpha del T by del T. So this is the governing equation for the one dimensional heat flow inside the pipe. The heat is flowing in the axial direction. Next, we will consider the cylindrical coordinate system only, but this time heat flows in radial direction. Suppose this is the cross-sectional area of the pipe, and we are assuming only there is heat conduction in the radial direction, and assuming that there is no axial conduction. Okay, and there is no change of temperature with respect to theta. So these are the assumptions. So temperature will be function of, since heat is flowing in the radial direction, there should be a temperature difference in the radial direction. So temperature will be a function of r and t. So again, starting with, so what will be the coordinate that in the previous case the coordinate which we are interested was x. Now here it will be coordinate is r. So we have to write the governing conduction equation in one dimensional for r. Okay, so 1 by a del by del r area times del t by del r plus all of the terms will remain the same. Okay, in the radial direction or for the cylindrical case, the area will be 2 pi times r into L. Okay, okay, and r can vary from 0 to r. So this will be the area which will be facing by the heat when it is flowing out of the cylindrical body. So this cylindrical body, we can think of it as a wire, solid wire or solid rod. Okay, and or heat flow when there is a pipe flow, and assuming that there is no heat conduction in the axial direction and heat is flowing only in the radial direction. So we can think examples like that. So putting a as this value in this governing equation, we can have 1 by 2 pi RL dou by dou R 2 pi RL del T by del R plus QG by K 1 by alpha del T by del T. Since 2 pi L all are constant, they will be cancelled. So only 1 by R dou by dou R times dou T by dou R plus QG by K is equal to 1 by alpha del T by del T. We will be getting. So this will be the governing equation when heat is flowing radially through a cylindrical body. Okay, and by solving this governing equation, we can find the temperature distribution along the radius if we know the boundary conditions. Okay, so next we will see the spherical coordinate system. Mind that we are all talking about only the one-dimensional case to simplify the system. And heat flows. Heat can flow only in radial direction for the case of spherical coordinate system. Mind that. Okay. So in general, heat can flow only in radial direction. So we consider this as the two-dimensional view of the sphere, and heat is flowing in the radial direction because the temperature difference in the sphere in radial direction. Since there is a heat flow in the radial direction, it means there must be a temperature difference in the radial direction. It means T is a function of, again, R and T, and the area which will be facing by the heat flow when it is flowing radially out of the this spherical shell. So it will be a sphere of radius R. That will be the area that will be facing by the heat flow. Since heat is flowing in radial direction, an area is dependent on R. Okay, so it depends on the direction in which heat flows. Okay, so again we can start from the governing equation, general governing equation. A times dou T by dou R plus QG by K 1 by alpha dou T by dou T. Okay, so area we can substitute as 4 pi R square here, and we get 4 pi R square dou by dou R times again 4 pi R square dou T by dou R plus QG by K is equal to 1 by alpha dou T by dou T. Since 4 pi is not dependent on R, so we can cancel it, and when we are left with only 1 by R square times